All right, this screencast is going to look at putting together the idea of the ion formation of the cations and the anions and actually show the two of them going together to create a bond. So the moving of electrons is really what makes a bonded compound. So I'm going to start with an example with potassium. So again, down here on the table, and again, if you know your charges, we're looking for a +1 here, and we're looking at fluorine over here, which is in our -1 group. So we know that to be +1, we have to lose 1 electron. So this 1 electron from potassium is going to go over here and fill in for fluorine. So one way that we can represent this is by showing that K plus has the electron configuration of argon and F minus has 2s2, 2p6, which is actually the electron configuration of neon. So this argon would have an octet as well. So both of them are doing that. So that's one way to represent bonding. Probably the most difficult. Orbital notation makes it a little bit easier to visualize. So I can show through orbital notation that this electron is being lost by potassium. So then potassium really looks like it has no valence electrons, but really remember it has what argon has. So that is the one advantage of writing out the electron configuration or doing the whole orbital notation. For fluorine, again, when we add this one, it's going to have its octet, and this now becomes a negative ion. For our next example, we're going to look at aluminum. So this time, aluminum has 3 valence electrons, okay? And fluorine, again, still has those 7. I'm using that same one. So if I take one of these valence electrons and plug it in over here, I am going to get then my fluorine minus, same as we did last time, with 2s2, 2p6. So this is fine with its octet, but this aluminum still has these 2 electrons. So it needs to get rid of another one. So I actually need to write this fluorine again. And put one of those down here to make this 3p6, and the third one from here. Now you can see that this gets a little more difficult to kind of follow. So although this works, it's probably the least productive way of showing this. So if we come down to our orbital notation, much easier to see what's going on here. So I'm going to take this one and I'm going to bring it over here and put it in there to make my fluorine ion or fluoride. So as soon as I do that, this becomes negative. Okay, and I need some place for this electron to go, so I'm going to write that multiple times. Okay, and this electron, it can come over here. And I need a place for this electron to go, so I'm going to do that one more time. And again, you can see how this gets very cumbersome when we do this as well, but this electron needs a place to go. So when we write the formula for aluminum and fluorine, it's going to have to be AlF3. So this is why some compounds have more than one number in them. If we go back up to Kf, it was a 1-to-1 ratio, so that's its formula is just Kf, but this one is a 1-to-3 ratio. Now, again, very cumbersome to draw all of this. So if you remember, we did electron dot diagrams. So if we go back up to our diagrams here, I'm going to do this off to the side. Potassium would have 1 dot. Fluorine, I'm going to make these X's just so we can tell the difference, is going to have its 2s and then its 5 p electrons, or its total of 7 valence electrons. And it's very easy to show that 1 dot going over 1-to-1 ratio. This is Kf. When I do the same thing with aluminum, I have my two S's and my P, and I'm going to have my same X's for fluorine. Okay, I can see that one electron's going to go here, and then I just need to keep drawing fluorine. So again, I still have multiple pictures to draw, but you can see that this is much faster. And I keep doing that until I get rid of all of the metal's valence electrons. And each of my nonmetals has an octet. This last example, I'm just going to skip to the electron dot diagram. So for magnesium, I'm going to have its 2 electrons. Okay, and I'm going to go out here to nitrogen and draw its 5. So again, 5 valence electrons from the group number. And again, which one you do X's and which ones you do dots doesn't really matter. I'm just trying to distinguish whose electrons are whose. So metals give to nonmetals. So again, think of the guy giving the engagement ring. So my first one's going to go here, and then I have a second one that's going to go here. Now, magnesium's gotten rid of all of its valence electrons, but nitrogen still has one that it needs. So it only has 7, it doesn't have its octet. So when you do have this situation, you just have to draw another of the positives, and you're always going to stick with the same element, so I can't just throw a different element in to fill that in. Okay, and that's pretty bad placement. You want to try and have those close so they look like a pair. Okay, and that means magnesium has another one to give, but now nitrogen has all 8 of it, so I have to draw another nitrogen. So I'm going to put this one here. Now, you'll see this nitrogen still needs 2, so I'm going to keep going with that. I need to draw another magnesium. And at this point, you know, it seems like it goes on forever, but it does eventually work itself out. And this one is going to go here. And that gives me a formula of Mg3. And 2, because I have 3 magnesiums and 2 nitrogens. Okay, the next activity you're going to do is sort of getting the charge idea from this. So if I were writing magnesium as an ion, again, I can use my table. It's kind of, this is all explaining what's happening at the bonding level, but we want to get a little bit faster at this. So again, nitrogen has 5. So if I do my number line backwards, or 5 minus 8, I'm going to get -3. So you're going to be looking at how we transition from the dot diagrams or the valence electrons to the charges, and then putting formulas together so that we can do this very quickly.